Okay, so the next unit that we're going to get into is Chapter 19 in our textbooks. And Chapter 19 deals with acids and bases. So we're going to get into talking a little bit about how we can use indicators. Our labs are going to relate to using indicators to differentiate acids and bases. Some of the different reactions that take place with an acid and a base, and or reactions with acids and bases getting together. So let's just really talk a little bit about properties. I would mention this, certainly the difference here. We would never want to taste any of the acids or bases that we're going to see in a lab, but certainly there are acidic and basic substances, and their tastes are this way. An acid is sour, so your lemon juice, lime juice, your citrus juices, a little bit of sourness to them. And bases are bitter tasting. I always define the bitterness as kind of like that, a little like chalky, like when you get that chunk of unsweetened chocolate when you were a kid and you thought it was just a chocolate bar, and you take a bite and it's just deathly bitter. So there's your taste. Feel, again, not certainly something to talk about when we get into the chemistry classroom, but acid, sticky, you get some lemon juice, lime juice, orange juice on your hands, on your skin. It is going to feel sticky versus a base, slimy, slippery type of substances. Reaction with metals. An acid does react with a metal, and a base not so much. So just a quick little example, acids, let's say we use an acid like hydrochloric acid, okay? We're going to see shortly that all acids are going to have this hydrogen ion, okay? So you're going to have the H plus ion, whether it's hydrochloric acid, here's sulfuric, H2SO4, again it has that H ion with a negative ion as well. So you always have an H on an acid, and we'll see that as we move along, but all acids have that H ion. And so if that reacts with a metal, it could be anything, let's say zinc, and you're going to have a single replacement reaction. And so every time there's an acid with a metal, it's a single replacement reaction. We know that hydrogen is a positive. Let's say zinc is a 2+ for our purposes here. It's going to want to get together with the chlorine. So we'd get ZnCl2, and notice what's left over, H2 gas. So since all acids have this H, we're always going to get this hydrogen gas being released as a product in a reaction with a metal. What's cool about hydrogen, I say cool, I don't think these folks would think it's cool, but this is, of course, the Hindenburg disaster. The Hindenburg was a German airship, Zeppelin, that was filled with hydrogen. And you can see, just in this quick little picture, if you haven't seen the video, just a disastrous reaction of what hydrogen does when it's exposed to flames. Hydrogen is super flammable. So, again, awful nasty. But again, that's a property of acids and bases. Bases won't react with metals. I'm putting conductivity here. Conductivity doesn't differentiate. Both acids and bases conduct. And I'm going to put litmus paper or other indicators. In litmus paper or with litmus paper, acids turn red and bases turn blue. There are two different types of litmus paper. We have red litmus and blue litmus, but both of them, whether they're red or blue, are going to turn red in an acid and blue in a base. So blue paper would stay blue. If it's red litmus paper, it will turn blue. So that's a couple little properties of acids and bases. We're going to see more as we move along with different labs. Quickly defining acids and bases. There are a couple of different definitions. The Arrhenius definition says that acids produce H plus and base produces OH, which again, as you heard me say, if, oops, let me just go back here before I show that. Acids produce H+, it means they have to have an H+, and bases produce OH, it means they have an OH. Now the Bronsted-Lowry is a little bit better because it says that an acid is an H+ donor and a base is an H+ acceptor. There are some bases that don't have an OH, and since they don't have an OH, then it may not necessarily produce the OH. So the Bronsted-Lowry is a little bit better where it says it's just an acceptor of an H+ ion. Okay? Now you saw quickly that water can act as both. Notice that when we break water down, we're breaking it down into the H+ ion and the OH- ion. So notice that defines both an acid or a base. So water can act as both. And what happens is when we have an acid with water, so here's an acid, hydrochloric acid, with water, we're not getting a reaction, okay? This is not a double replacement. It's not a reaction where, you know, we're going to switch, because obviously, notice H plus Cl minus, if I go H plus and O2 minus, then we're just going to end up with the same exact thing. So we're not going to have a reaction, but rather the H is going to act as an acid, meaning it is an H plus donor. In this case, water is going to act as a base. See how it can act as both. In this case, since it's with an acid, it's going to act as a base, meaning the H plus can get donated to the H2O. That means that our product is at H3O with a plus charge. Notice that H2O, just H2O. If you add an H to that, it's now H3O. And since it's neutral initially as H2O, when you add an H plus, it becomes H3O with a plus charge. Then whatever's left over, in this case, it would be just the Cl minus sign. So every time we have an acid with water, it's going to donate that H, and you're always going to get this. This will change the Cl minus, since of course your acid doesn't have to be hydrochloric acid, but this H3O plus, which is called the hydronium ion, will always be produced. Okay, so that's how it acts. That's how water will act as a base. Let me show you how water will act as an acid when it's with a base. So here's a base, and so we're going to add water to that. And again, it's just a dilution, it's not a reaction. In this case, water's acting as an acid. And so notice H plus, OH minus, the H is going to be donated. Acid is an H plus donor. Notice that since it's acting as an acid, it's going to donate its H. And in this case, you're always going to get the OH minus. And why we always get that is because we have HOH in the water. If the H ion gets donated to the base, then you're always going to have the OH minus sign. The other thing, H, NaOH. I'm just putting the H in front. I know some people might say, well, why don't you just put NaOH2? I like putting the H in front and then NaOH. And of course, it does have a positive charge because the H plus is what you're adding. This changes, and it changes depending on the base. The next slide and next discussion, I'll talk a little bit more about it. But that's how water can act both as an acid or a base.